These are some impressions of what could be possible with the next generation of 3D printing slicers. Completely overhanging surfaces without the need for any supports, printed on a standard machine. I'll tell you why current slicers are dumb, how you can try out the next generation of slicing, and how even you can contribute that they become a reality soon. Let's find out more. Guten Tag everybody, I'm Stefan and welcome to CNC Kitchen. This video is sponsored by Squarespace. Easily create the website you've always wanted or replace your old one that you've always hated. Save 10% by visiting squarespace.com/cnckitchen. Current 3D printing slicers are dumb. What I mean with this is that even though they are slicers for 3D printing, they simply stack two-dimensional layers on top of each other to form your final part. There are basically no movements within the G-code instructions where all three axes move simultaneously. That's why current 3D printing slicers are rather 2.5D slicers. But why are they using this approach? Well, simply because it's mathematically easy, and honestly because this approach works remarkably well. Yet we are leaving a ton of potential on the table because 3D printers are easily capable of complex three-dimensional moves, yet we don't have any software to take advantage of it. Over the last few years, 3D printing slicers didn't really change a lot besides being way easier to use and much quicker. Yet the general slicing approach always stayed the same. Cut a three-dimensional part into a two-dimensional slice, draw the perimeters around the circumference, and fill the rest with one of many infill patterns. The only real evolution we have seen this year is the Arachne perimeter generator, first seen in Cura, that dynamically adjusts the width of the extrusion for more details and less gaps. Still, everything is on a two-dimensional plane, which causes the typical stair-stepping patterns on sloped surfaces and of course requires supports on overhanging structures. Over the years, we have seen a couple of approaches of non-planar slicing, often to improve top surfaces, yet none of them ever really made it into a mainstream slicer. Though quite recently we have seen a couple of really impressive ways of 3D printing parts that have previously been deemed impossible by using really clever slicing approaches. One of them is non-planar conical slicing. A bunch of weeks ago I've shown this technique in my Rodbot video, where I visited the University of Applied Science in Winterthur, Switzerland, where they built a 4-axis Prusa printer that can manufacture complex overhangs without the need for support structure. Yet the best thing is that we can use the same slicing approach on a regular 3-axis printer to achieve very similar results. And this isn't just an idea published in a paper, but you can download the Python script necessary and try this out on your own parts and prints. I also uploaded a bunch of sample G-codes and printables for the not so programming savvy. If you print them or even slice your own parts, please share the results and spread the awareness around this method, and maybe consider subscribing to the channel for more like this in the future. So let's quickly talk about the idea behind this approach. Common FDM 3D printers are able to print quite steep overhang angles, yet at some point, particularly below 10 or 15 degrees, the plastic will just be extruded into free air, drooping down and ruining your print quality. This novel slicing approach tilts the layers a tiny bit, so that even when printing horizontal overhangs, only maybe the outermost perimeter is printed in mid-air, yet still sticks and is supported by the perimeter next to it. This way you can print even these extreme geometries without the need for supports. The conical slicing approach, which stems from the Rodbot project, even improves this concept and tilts the printing layers around a central axis and therefore forms a cone. Since we'll be printing our part on a regular printer instead of one with a tilted print head, there are some essential things that need to be taken care of, and one of them is nozzle clearance. Conventional 2.5D printing only needs to make sure that the nozzle is the lowest part of the print head, because we're only printing on a plane and nothing besides warped plastic should stick up. When we're printing with non-planar G-code, there will be sections of the print that will be on a higher level than the current print moves. This is why before we start the first non-planar G-code, we need to figure out what the maximum slope angle of our print can be. Unfortunately, many current printers only allow tiny slope angles because of their cooling system that reaches down almost to the print plate. The only printer that I had that worked acceptably out of the box was my Prusa Mini, which has quite a high part cooling shroud, and if you print small parts, allows up to around 20 degrees slicing angle. Bigger parts will still crash into the bed leveling probe, and I often just pushed it up after the leveling process. For other machines like all the Ender 3 derivatives, a really simple solution is just to use a longer nozzle, like one of these airbrush nozzles, to which I put a link down in the description, or simply a regular volcano nozzle. This looks a bit weird, but works better than one might expect. Just remember to move your end stop. Unfortunately, cooling is not the best this way, even though it's quite essential for printing these extreme overhangs. The airbrush nozzle is a bit better here because it's only a little longer than a standard nozzle, therefore still closer to the initial cooling location. So if you want to try this out, make sure you have enough clearance and optimize cooling as much as you can. But which slicer can you use to create this tilted G-code? This is the cool thing about this method, because you can basically use your own favorite slicer for this. The thing is that there is no simple checkbox for conical slicing at the moment, and you need to trick your slicer into generating conical G-code with a clever trick. We simply use 2 Python scripts for this, and I'll go over how you can easily do this yourself in a second. The first code is predeforming the STLs in a reverse cone shape by simply moving the points of the mesh upwards depending on their distance to the center axis. Then you slice the slightly weird looking part in Cura, Prusa Slicer, Simplify 3D or almost any other tool, and use a second script to back transform the movement commands within the G-code file to end up with a conical G-code that's ready to print. It's really simple. If you want to try this out yourself, all of this is open source and was developed by the ZHAW in Switzerland. During making this video and working with their code, I created a fork of this project to make it in its current state easier usable, fix some bugs and add some features. Nothing really crazy, but in my opinion it works better. I linked everything in the description. The code that we'll be using is in the scripts for variable angle folder. So here's the process, and I'm using Super Slicer for this demo because it has some additional features over Prusa Slicer, and most importantly has a switch that lets you export G-code with empty layers, which is sometimes really handy for this method. I load my STL file into the slicer with a slightly adjusted printer profile where the bed origin is in the center. I move my part so that the global Z-axis represents the axis of the cone that I want to use for slicing, and save the part in this new location. In the transformation script, I set the slicing angle and run it, which spits out the predeformed STL that's ready to be loaded back into the slicer. Now I make sure that the cone axis of the STL is again at the origin of the coordinate system, and then simply slice my part and save the G-code. Then I paste the name of this G-code into the second script, make sure that the right cone angle is set, and hit run to start the back transformation. And that's it, ready to run conical G-code generated in a minute. I also wrote a comprehensive guide on my website through which you should go step by step to ensure that you can get out nice G-code, because some essential things need to be taken care of. One of the huge pain points of Prusa Slicer and Cura is that they don't position the parts in their local STL coordinate system, but choose one themselves. There is a switch in Prusa Slicer that should get around this, but it seems to have been broken for a while, so please guys, fix that, because currently I need to use a ton of trickery to position non-symmetrical parts properly. The approach is not perfect, still buggy and requires a bit of manual work, but demonstrates how this novel slicing technique could be implemented into a regular slicer. Yet, conical slicing won't fix all of our overhangs and support problems at the moment. If you have watched carefully, you will have noticed that most geometries I've shown so far only had outward facing overhangs. Any inward facing overhangs actually would need even more supports, as with a regular 2.5D slicing approach. The current script also allows slicing parts with an inward cone, yet if your part has both outward and inward facing overhangs, you will need to slice the section separately and stack the G-code manually. If you have both inward and outward facing overhangs on the same height, you won't be able to find a solution at all. And this is one of the main limitations of conical slicing in its current state. It works great for special geometries, but will probably not be as impressive for any arbitrary geometry. What we'll need in the future are algorithms that automatically section the parts, depending on their geometry, and set individual slicing angles and orientations. An implementation I could imagine in the future is identifying geometries by their overhang angle and slope angle and calculating the ideal slicing angle for supportless overhangs and smooth top surfaces. In between, you can interpolate. This field could then be used to predeform the STL and also used for back transforming, giving us non-planar G-code even with variable layer height. I'm not the first one to come up with such an idea, and you can find plenty of papers on approaches and algorithms. Unfortunately, I don't have the time and probably the skill to do this myself, but I want to spread awareness of how much potential there still is in slicing software for FDM printing. So if you are a skilled enthusiast with too much spare time or a student looking for a thesis, maybe consider if a proper non-planar slicing integration is the challenge you've always been looking for. Anything that we as a community can release and contribute open source is something no one else can patent. Yet, if you are a software company, also think about if you want to be the first one to do non-planar slicing with your tool. I was happy 6 years ago to pay for Simplify 3D because it did the best supports at that time. And I'd honestly be happy to pay a reasonable amount for a next generation FDM slicer. Yet, new slicing methods, especially non-planar, will also require adjustments in hardware of printers. And this is why I think that we won't see this being implemented in Prusa Slicer and Cura soon, because their machines, especially their printhead, are not yet optimized for that method. Something you have already seen plenty in this video is the clearance around the nozzle, so that non-planar moves are even possible without crashing into the print. Also, how should the tip of the nozzle itself look like? Because the bigger the flat, the more it will interfere with the extruded plastic. Yet, the smaller it is, the less ironing action we will have, and material will squish out to the sides. And then there's the Z-axis. When this axis is involved in every print movement, it will need to move way more than in a regular print, and probably wear out quicker with a common lead screw approach. And of course, cooling also plays a major role if we want to print supportless and need to cool down the plastic as fast as possible. So there's still a ton of really interesting research and development necessary until we see non-planar slicing in all of our prints, but I think we have finally reached a point where proper implementations are really close. I'd love to hear your thoughts on the conical method and non-planar slicing in general. Do you think the current 2.5D slicing approach is just good enough? Or do you also see this huge potential in new algorithms? Please let me know in the comments below. And I highly encourage anyone interested in this method to check out my detailed website article that goes over the steps so you can get this method working on your setup and potentially contribute to it in the future. It's sometimes just impossible for me to squeeze all of the detailed information into a video and still keep it entertaining. And this is why I'm so happy that Squarespace, who sponsored this video, provides easy to use tools to create additional content on my website just for you. Squarespace is the leading website creation tool that we've been using for years on our own website. Gone are the days where you had to know HTML, CSS, or what an FTP server is to create a website. Squarespace takes care of everything, and with their intuitive tools, creating a beautiful website is easier than writing a Word document or creating a PowerPoint presentation. It doesn't matter if you're a maker, an artist, or a business that wants to sell products or just present yourself in a modern way. Squarespace has beautiful templates that you can use as a starting point and then customize them to your needs. You can add a blog, an online store, offer mailing lists, or even members-only areas where you release special content for your paying subscribers. All of this is affordable and easy to use, and if you're still getting stuck, they are offering great 24/7 support and one of the best help centers that I personally have ever used. Try it out for free by browsing squarespace.com/cnckitchen and get 10% off your first website and domain purchase if you use code CNCKitchen on checkout. Create the website you've always wanted or replace your old one that you've always hated. Go to squarespace.com/cnckitchen and use code CNCKitchen at checkout. Thanks for watching, everyone. I hope you found this video interesting. If you want to support my work, head over to Patreon or become a YouTube member. Also, check out the other videos in my library. I hope to see you in the next one. Auf Wiedersehen and goodbye.